happens when I have a physical implementation that maybe sits with discrete chips, and then how do I kind of look at that circuit and kind of analyze what's going on. And in particular, I want to look at a case here where I'm talking about I actually have shift registers in the block. And so it wouldn't be uncommon to find I'd have an older form structure that might have been built with, oh, I don't know, CMOS inverter chip, some NAND and NOR gates, and a couple basically shift register blocks. So there's 7474s that have two shift register blocks in it. And I might have all of this sitting together in a wire in some sort of breadboard fashion, or have various connections in this breadboard. Not uncommon, but then you'd say, well, I'd really like to be able to take this and understand it, analyze it, and then I'd probably eventually put it into some other form. Maybe it's VHDL code that I can put on an FPGA, maybe it's something I put on a custom chip, who knows. So I wanted to look at something with a simple shift register and kind of talk through what that might look like. Well, if you look at the structure, it turns out we have actually what looks like 5 inputs and 2 clocks. Now the first thing is if you extract this entire circuit out, what it turns out is I've got 4 shift register blocks. This is not surprising given that there are 2 in each 7474 series chips. Fair enough. And then in addition to that, I've got some inverters and some NOR gates being used here. And what's interesting is I have a whole bunch of different pieces here. Those parts, when I extract it out, gives me this very interesting logic, which if I look at it closely, is really a 4-input NOR gate. But it basically is a way to extract it out with some very basic components there. 4 inputs between what is these 4 states of the registers, which is A, B, D, and E. And those are the pins that when I'm trying to extract it out, I go, oh, there's an A, B, D, and E here. I should try to figure this out and try to work with that. Of course, there's an A, B, E, and D here also on the registers. So you'd have to make sure you've got both of them. There's this interesting point, which is C, which is an input, which is basically designed to just clear the register. So if I actually have, if I assert, and this is actually going to be negative logic, if it asserts it, it'll just clear, which basically makes the state Q of each of those registers just equal to 0. Interestingly enough, what does the NOR gate do? Basically, if A, B, D, and E are all zeros, the probe point, this thing that's going into that first input, is a 1. Otherwise, it's a 0. So how would you think about that differently? What you think is, wait, if I have at least a 1 that's propagating it through this register set, I'll basically not have to feed anything but a 0 in here. But only when it's completely empty would I put a 1 here. So what's going on? Well, once I put the 1 in, that, say it all starts empty, I clear it, it just starts off 0. I bring in the 1 propagates to A, to B, to D, to E, then everything is 0, and then it feels like it kind of just resets itself. And this is a very interesting structure. It's called a scanner structure because often you use this if I want to multiplex many different components and put them on a single output line. This is a really good circuit to kind of create all of those digital lines. So this works out well. And what's interesting is with a little bit of look on this, I can actually take a look at it and I go, well, I got 2 clocks. And notice that they're not only clocks that are alternating, but they're actually non-overlapping. There's a region for both of them that they're at 0. And this becomes extremely important because if you look at it, I want to be able to load the value into D, so therefore it actually holds that register so that way the next register can get hold of it and get to that, and then the next one and the next one. If I put all these on the same clock, it turns out that you might get a case which is transparency, which is I write into that latch and then it'll actually get to Q and it'll just keep writing all the way through the structure, which is not what I want. And so if I look at the logic structure here, I got clocks that go up and they're alternating through here. Clock 1, clock 2, clock 1, clock 2. And I can just demonstrate the clear signal. So as when it's 0, it makes everything clear, just kind of a nice way to start. You can see that the probe actually starts high and then falls. There's a 30 millisecond delay in there. And then what you see is the sequence of A, B, D, and E proceeding. When there's nothing there, the probe kicks in, gives me a value I can load in, and I get A, B, D, and E going again. So this is kind of a neat approach that you can see, but you can also see how you can start from what is a basically interesting circuit with very limited documentation and go, oh, here's what's going on, and I can put it all together and understand it.